Okay, so good morning everyone. So today we will revisit the theory of parsing. Specifically, the topic for today's discussion is parse trees and ambiguity. Okay, so in the last couple of classes, we have seen how to design a scanner. Okay, so what the scanner does is it takes the source code as input and it tokenizes the input. Okay, and in fact we have seen the way it works is the parser asks the scanner, could you please pass me the next token, and the scanner gives the next token to the parser. So the scanner and parser, they work in an interactive fashion. And the parser takes the stream of tokens from the scanner and it checks if the program is syntactically well formed or not. If the program is syntactically well formed, then it outputs a intermediate representation of the code, which is usually the abstract syntax tree. And if the input has any syntactic errors, then the parser outputs relevant diagnostic information. Okay, so this is what the parser does. Going on. So, and then we have also seen that context-free grammars are very good tools to specify the syntactic structure of programming languages precisely and concisely. For example, in a very simplistic programming language, we can say, you know what, a program is a sequence of statements. So a program is a statement list. Okay. And what is a statement list? A statement list is either a statement or it is followed by statement followed by statement list. An important observation here is we are defining statement list in terms of statement list in the second production here, in the second production or substitution rule here. So there is a recursive definition happening here with respect to the statement list non-terminal symbol. But what is important is there is also a alternate substitution rule or protection rule where we are defining statement list without referring to statement list. Okay. This observation is important because in the absence of the first substitution rule here, so the definition is not complete. There is no way to terminate the recursion. Okay. So this is one observation. Next is, so now if you look at the definition of a statement list, if you look at the definition of a statement can be an assignment statement, okay, or it can be a method call, or it can be an if statement, or it can be an if then else statement, or it can be a while statement, or continuous statement, or it can be a block. And what is a block? A block starts with a left flower bracket followed by that there could be a variable declaration list followed by statement list. So if you look at the grammar in this slide, so all non-terminal symbols are defined except for 2 or 3 non-terminal symbols. The first non-terminal symbol that is not defined is location. The second one is expr. The third one is variable declaration list. Okay. Again, it's easy to define to what these non-terminals, what structures these non-terminal symbols can take. Okay. So moving on. So here we can see in this slide the definition of a expression. An expression is you take two expressions and connect them through a binary operator, you get an expression. Or you take an expression and you put you apply a unary operator, you get an expression. Or you put this exclamation or negation symbol, you get an expression. Or if you put parentheses around an expression, you get a new expression. So this is how we are defining the expression. Okay. So the idea here is context-free grammars. They help us in specifying the syntactic structure of programming languages precisely and concisely. Okay, so that is the idea. So now, given the syntactic structure of a programming language in the context-free grammar, we want to move on to the next problem. Okay, so that is, so we want to check, given a string W, we want to check if this string W belongs to the language described by the grammar or not. Okay, and this is what the theory of parsing is all about. Okay, this is what the theory of parsing is all about. Okay, so just for again, I would like to recall. So we have an example context-free grammar here, and formally a context-free grammar is defined using uh, as a four tuple. Okay, so it consists of a set of non-terminal symbols represented by n. Okay, set of non-terminal symbols. In the example grammar we have here, the non-terminal symbols are goal, expr, and term. Okay, and among the non-terminal symbols, there is a special symbol called as a start symbol that is denoted by S. In the example grammar that we have, goal symbol, the non-terminal symbol goal is the start symbol. Okay, and then there is a set of terminal symbols, okay, which is denoted by T. In the example grammar that we have, we have four terminal symbols: number, ID, plus, and minus. And P denotes a set of substitution rules or production rules. Okay, so here in this grammar, we have on line 1, we have one substitution rule or production rule. And on line 2, we have two substitution rules. Line 3, we have again two substitution rules. Line 4 also has two substitution rules. Okay, and how does a substitution rule look like? A substitution rule looks like this: A goes to alpha. And the notation that we use is, so all non-terminal symbols we denote by using capital case letters, English alphabet like A, B, C, D at the beginning. Okay, which occur at the beginning of the English alphabet, we use to denote non-terminal symbols. This is the notation that we use. And lowercase Greek letters, they indicate strings over non-terminal and terminal symbols. Okay, this is what we have. Like, so a substitution rule looks like A goes to alpha. Okay, so I want you to remember this notation, that whenever you see capital case English alphabet occurring at the beginning, like A, B, C, they are non-terminal symbols. And whenever we use notation such as alpha 1, alpha 2, gamma, etc., they denote strings over non-terminal and terminal symbols which occur on the right-hand side of the substitution rules or productions. Okay. So now, so remember our question that we are trying to answer is, given a string W, we want to check if W belongs to the language described by the grammar or not. Okay. So the process of deriving strings by applying productions in the grammar is called as derivation. Okay, like for example here, or this process of discovering the derivation is called as parsing. Okay, so parsing and derivation. So for example here, let's take the string ID plus number. So this is W. Okay, this is our string W. Okay, we want to check if this string W, it belongs to the language described by the grammar. So what we do is we start with the start symbol. And then if you see from start symbol, there is only one substitution rule that you can apply, that is goal going to expr. Okay, goal going to expr. So you apply the substitution rule, you made one step progress in the process of derivation. Okay, so now, so we are at expr and we want to move forward. So now we look at what are all the substitution rules that are available for the non-terminal symbol expr. There are two substitution rules possible. Okay, so we have to choose one of these two substitution rules. So here we have chosen the first substitution rule, that is expr of term. So from EXPR, we went to EXPR of term. So now from EXPR of term, we want to make further progress. Okay. So now we have a choice. So there are three non-terminal symbols here. Okay. There are three non-terminal symbols here. One is EXPR, the other is op, the third one is the term. So among these three non-terminal symbols, which one should we pick for expansion and move to the next step? So here we use a simple rule. So let's take the leftmost non-terminal symbol EXPR and then we try to expand it. Okay, so after picking EXPR for expansion, again we encounter this question among two substitution rules that are there here. This is one, this is two. Which one should we pick? So earlier we have picked the first substitution rule, but now we kind of magically said or picking that let's use the second substitution rule. So we are replacing EXPR with term and we arrive at here. Okay, this is where we are right now. And then again we have the question. So term of term. So among these three non-terminal symbols, which non-terminal symbol should we pick to move forward in the process of derivation? So we use the leftmost non-terminal symbol term. And then again, there are two possibilities for term, number or ID. So here we chose ID to go to the next step of derivation. Okay, so on and so forth. Okay, so finally, so we started with goal and we ended up with generating the string ID plus number, indicating that the string ID plus number is a valid string described by this context-free grammar. Okay, so through this example, we can see there are two important questions that we have to answer at each step of derivation. Okay, the first question is which non-terminal symbol to replace. Like for example, when we are working with EXPR op, there are three non-terminal symbols. Among these three non-terminal symbols, which one should we use to move to the next step of derivation? That is the first question. The second question is, once we chose the non-terminal symbol, which substitution rule to apply to expand or go further in the process of derivation. Like for example, here again, so we are trying to expand EXPR, but there are two possible substitution rules for EXPR and we have chosen the first. Okay, but whereas here, when we are trying to expand EXPR, we have chosen the first substitution rule to expand. Okay, so here in the second case, so here we used in order to move from here to the next, we used the substitution rule EXPR going to term, but here we used EXPR goes to EXPR of term. So how did we make this choice? Okay, is this magic or is there a systematic way to go about picking the right substitution rule? So that's an important question to answer. Okay, among these two questions, the first question is easy to answer. There's an easy answer to this, but second question is it's a difficult question, and we will try to address this question in multiple classes by taking multiple classes. Okay. So the first question, which non-terminal symbol to replace? So if we replace the leftmost non-terminal symbol at every step of derivation, then we call such a derivation process as leftmost derivation process. Okay. But on the contrary, it is also possible for us to pick the rightmost non-terminal symbol at every step of derivation, in which case we construct what are called as rightmost derivations. And we usually don't care about randomly ordered derivations. Randomly ordered derivations means in one substitution, at one step of derivation, you use the leftmost non-terminal symbol, and another step of derivation, you use the rightmost non-terminal symbol. In another step of derivation, you may choose a non-terminal symbol which is neither leftmost nor rightmost. So those are called as randomly ordered derivations, and we don't care about these randomly ordered derivations. Okay. So given a derivation, so we start from S, we finally reach W. Okay. See, as I said, we use lowercase Greek letters to indicate strings over non-terminal and terminal symbols. Okay. So gamma 0 to gamma n, we call them as sentential forms. And we use the notation that we are able to discover W from the start symbol S in 0 or more steps. So sometimes we use this also. That means we are able to discover the string W from the start symbol S in 1 or more steps. Okay, star means 0 or more steps, plus means 1 or more steps. And if the derivation is a leftmost derivation, then gamma 0 to gamma n are called left sentential forms. Okay. And if the derivation is a rightmost derivation, then gamma 0 to gamma n, they are called as right sentential forms. Okay. So now let me use whiteboard and okay. So let's take an example grammar. We'll start with a very simple grammar. Okay, so we have an example grammar. So the example, let me use so we have the grammar is E goes to E plus E or ID. This is the grammar that we have. Okay. And so let's say the string that we have is W is equal to ID plus ID plus ID. Okay. So now let's look at this particular derivation process. We start with E. So here the start symbol is E. So we start with E, and then the next step is we say E goes to E plus E. Okay. So as we do the derivation, construct the derivation, simultaneously we try to give a graphical representation for the derivation process. Okay. So for example here, so we represent it as E goes to E plus E. Okay. So now here, so we have E plus E. So what we do is we pick the first non-terminal symbol and then we expand it. Okay. So in order to make it clear, so this is what we try to expand here. And so in the tree representation, it will be this. So and then we go to the next step. In the next step, we replace the first E with ID. Okay. And then here we replace the second E with ID. And then finally we have this. Okay. So this is the parse tree. So this is what is called as the derivation that we did here is called as a leftmost derivation. Leftmost derivation. And this is associated parse tree. What we are doing here in the derivation process, we kept track of the same in a graphical form or in a tree structured form, and associated tree structured form is what is called as a parse tree. Okay. So now what we do is from the parse tree, we can recover what is called as a rightmost derivation. So how do we do? So we start from E. We start from the root. Okay, so the root, this is the root. So we start from the root, and then from the root, you can see the children of the root is E plus E. So from that, you can say this is E plus E. Okay. And then, so since we are trying to discover a rightmost derivation, we go to the rightmost child of the root and see how it got expanded. So here you can see this is the rightmost child of the root, and the substitution rule that we used here is E gets expanded to ID. Okay, so this is the substitution rule that we did. So now what we do is we say we do this. E goes to ID, E plus ID. Okay, so I want you to observe that when we are moving from here to here, okay, we are replacing the rightmost non-terminal symbol. Okay, so now again, so we are here and we can see that the child for this particular non-terminal symbol is the E plus E. Okay, so what we do is we apply the same E plus E side. Okay, so now our focus is on at this level. Okay, so E plus E. So among this E plus E, this one is the rightmost non-terminal symbol or rightmost child for this parent node E, and we see that this E is expanded using the substitution rule. E goes to ID. Okay, so what we do is we replace it with, okay, and after that we come here, we come to this non-terminal symbol and we note that it got expanded using the substitution rule. E goes to ID, and then again we replace it. So here if you can see that on the top we started with the leftmost derivation, and then we went to we constructed an associated parse tree, and from the associated parse tree we are able to recover a rightmost derivation. Okay, so this is the thing, leftmost derivation to parse tree. Okay, from parse tree we constructed the rightmost derivation. So what is important is you might as well start with the rightmost derivation, okay, and you can construct the parse tree, you get the same parse tree. For this rightmost derivation, the associated parse tree will exactly be the same, okay, and the associated leftmost derivation will also be the same. Okay, so either you start from the top and go to bottom, okay, or you start from the bottom or go to top. Okay, so it will be the same. You will end up having this what you are seeing on the screen. It will exactly be the same wherever you start in the screen. That is, you start from the top, you go to the bottom, you start from the bottom, you go to the top, or you even construct the parse tree. Okay, and then generate from the parse tree, you can construct a leftmost derivation, and from the parse tree you can construct a rightmost derivation. No matter where you start, you will end up having the same leftmost derivation, parse tree, and rightmost derivation. Okay, so this is an important observation here. All right, any questions? Let's see if there are any questions. If there are any questions, you may ask in the chat box. Okay. Okay. So if you are doing good, so let's see. There is one question. Can you unmute yourself and ask the question, because I am not able to see the chat box for some reason.
Hello, sir. Am I
Yeah.
audible? Sir, my question is, parse tree is always unique, or there is more than one parse tree possible for a grammar? Means,
Is
for
there
a
more than
W,
one parse
sorry.
tree?
Yeah, for a W, if there is a possibility that generate two for more
Yeah,
time.
sure. I will answer that question. Good question. Okay. Yeah. So now, so let's move on. So there is a good question, and that's what I would like to answer next. Okay. So let's start with the same string, that is same grammar and same string. So we have, so this is the grammar that we are working with. Okay. E goes to E plus E and ID, and the string is W is equal to. Okay. So here, this grammar, if you see, this is the substitution. This is the, let's look at, let me draw a line here. E goes to E plus E, E plus E plus E, and ID plus E plus E, just to make it clear that this is the one that we are expanding. Okay. And then from here, we get ID plus ID plus ID, and the associated parse tree is this. Okay, so but then there is a different way to uh, do this. E goes to E plus E, and then so what we do is we can replace this E with the first E with ID. This is ID plus E, and then we can say ID plus E plus E. Okay, and what is the associated parse tree? This is the associated parse tree. Okay, this is associated parse tree. So here you can see there are two different leftmost derivations for the same uh, string. Okay, and then so since there are two different leftmost derivations, there are two different parse trees for the same string. So what happens is, if you construct an abstract syntax tree for this particular parse tree, this is the kind of abstract syntax tree you will end up constructing. Okay, so here, this is in this particular case, the semantics that we are giving to the statement ID plus ID plus ID is, first add the two leftmost IDs, and then whatever the result that comes, add it to the third ID. This is what is called as a left associativity. Okay, and here what we have, this is what is called as a right associativity. Okay, so depending upon the programming language semantics, okay, some programming languages may say when there is addition, like when there is an expression such as this, so perform left associative addition, and some other programming languages may say when you get an expression such as this, perform right associative addition. But all programming languages, as far as we know, they usually give left associativity semantics to expressions. So what we want is, we want to lean towards the parse tree, and the AST. This is the AST. This is the parse tree. So we want to lean towards the parse tree and AST that is there on the left hand side, where we are giving left associativity semantics to the input expression. Okay, so this is very important idea that parse trees are not only useful for checking the syntactic structure of programming languages, they also give during the process of parsing, they also give associated semantics by constructing the corresponding abstract syntax tree. Okay, so the grammar that we have right now, the grammar that we have here, this is what is called as an ambiguous grammar. This is an ambiguous grammar because two different parse trees are possible and two different ASTs are possible. So two different ways of interpreting the input program are possible. So this is not desirable. Okay. So we will see how to fix this. But before we see how to fix this, so we have to define this notion of ambiguity. So we say that a grammar is ambiguous. Okay. So I will give three definitions and we say that all these three definitions are equivalent. Okay. The definition one is, so we say a grammar G is left ambiguous if there exists a string W such that there are more than two leftmost, oh no, so more than one, yeah, more than one leftmost derivation. For the string, there exists a string W such that yeah, I think that's good enough. Okay, so yeah, right. So we can define a notion of left ambiguity. Okay, so we say that a grammar is right ambiguous. Okay, if there exists a string W with more than one rightmost derivation. Okay, and then we can have a third definition, that is we can say that a grammar is parse tree ambiguous if there exists more than one parse tree for the same string W. Okay. So it turns out that, so from what we have seen, since there is a one-to-one correspondence, okay, so you have seen before, so if you start with the leftmost derivation, so let's say we started with the leftmost derivation, this leftmost derivation gave a parse tree 1, and because of that we get a rightmost derivation 1. Let's say the grammar is left ambiguous, so because of that there is one more leftmost derivation LD2, it yields associated parse tree PT2 and then associated rightmost derivation RD2. So if a grammar is left ambiguous, then it is parse tree ambiguous and it is right ambiguous also. Similarly, if the grammar is parse tree ambiguous, then it is right ambiguous and left ambiguous, so on and so forth. So in general, we say, so finally, the claim is, we say that a grammar is ambiguous. So important definition is, we say a grammar is ambiguous if it is either, sorry, if it is either left ambiguous, okay, or no, parse tree ambiguous. I'm using shorthands. LA stands for left ambiguity, PTA stands for parse tree ambiguity, and RA stands for right ambiguity. Okay, so this is how we can say this is the definition of ambiguity for a grammar. Any questions here? I want you to appreciate the equivalence between these three. Okay. For every leftmost derivation, there is a unique parse tree, and for every parse tree, there is a unique rightmost derivation. So, and for every rightmost derivation, there is a unique parse tree, and for every unique parse tree, there is a unique leftmost derivation. So because of that, if a grammar is left ambiguous because there is a string with more than one leftmost derivation, then naturally the grammar will also become parse tree ambiguous, and it also becomes right ambiguous. Okay. So how do we solve this problem? Okay, how do we solve this problem? So let's take a bigger grammar, okay, and see how we can resolve this problem. So E goes to E plus E, E minus E, okay, or so this is the shortest, extremely concise way of expressing the structure of expression. Okay. Unfortunately, this grammar is super ambiguous. Okay. So there are many ways of, for given an expression, there are many ways of constructing a parse tree for that expression, and many associated abstract syntax trees, and hence many ways of interpreting the expression. Okay, so that means if you just take this grammar and then write a compiler for your programming language, then depending upon who wrote the compiler, depending upon one time when you compile the program, it may give you one output, and another time it may give another output. So it will all be chaos. So we want to fix the ambiguity problem here. Okay, so there are two ambiguities here. In order to understand the two ambiguities here, let's say you have a statement such as id plus id star id. Okay, so here what are the, so there are two ways we can easily see. There are two parse trees that we can construct for this. So one is so E goes to E plus E star E. Okay, so another way of doing it is E goes to E star E. This is ID. The AST for this one is, let's draw a line. The AST for this one is this. And we know this is what we would like to, this is the semantics that is given by most programming languages, because we want addition, multiplication to have higher precedence over addition. Okay, so star, sorry, 1 minute. Okay, so this is the semantics that we want, because multiplication has higher precedence over addition. So what the parse tree that we are looking for, or the abstract syntax tree that we are looking for, is what we have on the left hand side. Okay, so we have to, there are two ways of dealing with it. So one way of dealing with it is by rewriting the grammar. Rewrite the grammar. This is one way of doing it. There is a second way of doing it is tell the parser, you tell the parser, you know what, tell the parser your preference. You tell the parser that this is what you prefer. The parse tree or the AST on the left hand side is what you would like, and the parser will consider your preference and always construct a parse tree which respects your preference. Okay, and this is what you will be doing in your project, and this is what we will do most of the time in practice. Okay, this is the option 2 is what we usually do in practice. But for the sake of completeness, what we will do is we will also take an approach, okay, where we rewrite the grammar to eliminate the ambiguity in it. Okay, so let's see. So again, so that you can easily remember. So E goes to E plus E. Okay. So an important idea in rewriting this grammar to eliminate the ambiguity is this. Let's say if you have a statement such as this 2 star A plus 3 star B. So what happens is the associated AST looks like this. So in the AST, operators with higher precedence, they occur at the lower in the tree, and operators with lower precedence, they occur higher in the tree. So if you look at the statement 2 times A plus 3 star B, the highest precedence ones are 2A, 3B, because they are like the atomic entities in the expression. Because you want to first evaluate what is 2, evaluate what is A. What is evaluating A means reading the value of A. Okay, similarly, evaluate value 3 and the constant 3 and evaluate B. Okay, and then after that you go to the next, the operators which are of the next higher, next precedence level, and then now the higher precedence, and then you compute them. Okay, so here you do 2 star A, 3 star B, and finally you compute plus. So we have to keep this idea in writing our grammar. Okay. So the way we do it is, the idea is we say an expression is sum of terms. An expression can be a term or sum of terms. An expression can be a term. Let me or an expression can be a term or it can be a sum of terms. Okay. So that means what we are, so here, so this is a term, this is term 1, okay, so and then what we have here, this is another term, term 2. An expression is a sum of terms, that's what is the first story. Okay, step 1 is, so we say expression, an expression is a sum of terms. Okay, it can be, when we say sum, it means either plus or minus. Okay. And here, if you see, there are two ways of writing this E goes to E plus T. So like for example, let's take a simpler example. So E goes to E plus T, A, or so this is one grammar. So if you take this grammar and if you see A plus, if you consider something like A plus A, then what happens is this is E plus T, this is E plus T, this is T, this is A, this is A, this is A. The associated AST is this. So by writing the grammar in this particular way, that is E goes to E plus T, by writing the substitution rule in this particular way, we are giving left associativity semantics. Okay, but on the contrary, let me erase this. But on the contrary, if you write something like this, E goes to T plus E, T, and T goes to A, and then if the string W is A plus A plus A, then the parse tree looks like this. E goes to T plus E, this is A, this is T plus E, T, this is A, this is A, and associated AST is this. Okay. So this is a right associativity semantics. So the way we write this substitution rule, whether E goes to T plus E or E plus T, we either give right associativity or left associativity semantics to the expressions. Okay, I want you to keep this in mind. Right now, we want to give left associativity semantics to addition operator and subtraction operator. So because of that, we use the substitution rule in this particular form. That is, E goes to E plus T or E minus T or a term. Okay. So now an expression is sum of terms. What is the term? A term is a product of factors. Okay. A term is a product of factors. Again, here you have the option of writing T star F or F star T. Depending upon how you write, the corresponding associativity will be assigned to the multiplication operator. Okay, or it can be a factor. So here, a term is a product of factors. And what is a factor? A factor is an atomic entity. A factor is an expression within parentheses, or it can be an identifier, or it can be a number. Okay. So this is the rewritten grammar where the ambiguity is eliminated and the precedence rules given by the programming language are respected. So when we rewrite the grammar by eliminating ambiguity, usually what happens is we end up writing more complex grammar, which makes parsing a bit more harder, and it also makes construction of AST which little bit more trickier. Okay. But in practice, as I said, we usually handle most of the ambiguities, especially related to expressions, by not rewriting the grammar, but by telling the parser that, you know what, when you are constructing the parse tree, when you are constructing the AST, this is my preference. These are my precedence tools. You indicate it to the parsing algorithm, and the parsing algorithm includes your preferences in the when it is parsing an input and constructs the associated parse trees and abstract syntax trees. Okay. So now let's look at some more examples of ambiguity. This is related to, this is on expressions. So now let's go back to our presentation. And okay. Yeah. Yeah. So another source of ambiguity, for example, is this. So yes, great. We am able to write. There is So let's say you have a grammar such as this. A statement is if expression then statement, or if expression then statement else statement. So these are the two substitution rules. Okay. So let's say if you have a statement like this, if E1, okay, uh, then okay, so then what are the statement we have here? If you see the statement here, there are two ways of constructing parse trees for this statement. Okay, so this is the first tree. This is the parse tree 1. In the parse tree 1, what happens is the way it is parsed is the statement if expression 1 is true, okay, if expression 1 is true, then then execute this whole of this statement. If expression 1 is true, then execute the whole of this statement here. Okay. Another way of parsing this is, okay, that's what the parse tree, that's what the P1 approach, parse tree P1, that's what is being done here. An alternate way of parsing it is, if expression 1 is true, then treat what you have here, no? If then, if E2 then S1 as the if part of the outer if statement. Okay, so this is parse tree 2. Okay, so put it differently, what happens is in parse tree P1, the S2 is matched to, the statement S2 is matched to inner if. The statement S2 is matched to inner if. Whereas in the parse tree P2, okay, this is parse tree P2, the statement S2 is matched to outer if. Okay, so there is an ambiguity here. Okay, very bad ambiguity. It can lead to disastrous consequences in your program. Okay, so the semantics that is given by the programmer or the programming language designer is always match the statement to the closest if. Like for example, for S2, the closest if is the inner if. Okay, so the parse tree that is preferred is P1 as against P2. The ambiguity or the semantics given by the programmer is match statement to the closest if. So S2 will be matched to the closest if, that is the inner if. In this case, parse tree P1. So parse tree P1 is the preferable parse tree as against parse tree P2. So again, in order to handle this ambiguity, there are two approaches. The first approach is you rewrite the grammar. So this is the rewritten grammar. We will not go through this grammar. You may want to check whether this rewritten grammar takes care of the ambiguity. Not only it takes care of the ambiguity, it leans towards the particular semantics that is given by the programming language designer. That is, match the else part with the closest unmatched if. Okay, this is the semantics that we are looking for in the rewritten grammar. Okay. Now let's look at a couple of more examples of ambiguity before we wind up this class. So let's say there is a programming language in which, you know, like when you say fun, no, 2, 3, 2, A and array 4, C. So here, this is a function call and this is an array access. We are not using square brackets. Okay, in C programming language, when you are accessing, so here, let's say A is an array. In C programming language, we use square brackets, okay, for array indexing. But let's say there is a programming language where parenthesis is being used for indexing arrays. So when you look at fun2, A and A4, C, you don't know whether which of what is whether fun is a function call or whether it is a array index access. Similarly, the case with A. Okay. And if you see the associated grammar, they say the statement, the first substitution rule here says that a statement can be a method call. That's what statement 1 says. Okay, a statement can be a method call. And then if you see and then method call consists of ID followed by parameter list, and the parameter list is the list of parameters, and a parameter can be an ID, so on and so forth. And then here, if you see statement, the substitution rule 6, so here this could be an expression, can be an array index. Okay, so this is array index operation. So there is an ambiguity because we don't know when given fun2, A or A4, C, whether to construct a parse tree or whether to use the substitution rule 1, or to use the substitution rule 6. There's a problem. Okay, so there is one way of handling this ambiguity is if you know the type of the identifier before, like whether it is a function or the name of an array, then we can possibly take care of this ambiguity. Like for example, we can rewrite the substitution rule 1 by making it into function ID, and then here we can say ARR ID. So when an identifier is encountered, when the scanner encounters an identifier in the token stream, in the input stream, it goes and looks into the symbol table and checks whether the identifier is say of type function name or of type array. If it is of type function, then it returns function ID as the token type. And if it is if it's of type array, it returns array ID as a token. Okay. So in order to do that, the lexical analyzer has to construct a symbol table, and it has to keep track of the type of the identifiers in the symbol table. And for this to happen, the programming language has to enforce the rule that the identifiers, that all the identifiers which the programmer uses, they have to be defined before they are used. They have to be declared before they are used. Because if the identifier type is not declared before it is used, the lexical analyzer will not be able to say whether the identifier is a function or whether it is a array. Okay, in which case this ambiguity cannot be resolved. Okay, so this is what is called as a context sensitive ambiguity. Context sensitive ambiguity. The grammar, you cannot do anything about it in the grammar. Okay, and we can resolve it using type analysis. Resolve it using type analysis. The other way of handling this is you just let it go through the syntax analysis phase and construct an AST, and at the time of you do an analysis on the AST and fix the ambiguities. So another approach. Let the ambiguities be there. Resolve them in the semantic analysis phase. When more type information is available. This is another approach. Okay. So this is the summary. Okay, like so ambiguity arises from two distinct sources. So one is confusion in the syntax, context-free syntax. That is what we have seen with respect to expression grammar and with respect to if-then-else statements. And then the second kind of ambiguity is what we have seen just now. That is and in order to resolve that ambiguity, we require some context. Okay, and how do we resolve the ambiguity? So number one, you resolve the context. We rewrite the grammar. That is one approach. Okay. The other approach is you let the parser. You tell the parser to do the right thing. Okay, that is the other approach. And in order to handle context sensitive ambiguity, which we have seen just now, we need to know type information, and this is one approach. Knowing the type information. This is the first approach where the lexical analyzer looks at the symbol table and resolves the ambiguity. The second approach is what I have just said, that is you accept a superset of the language and then we resolve it in the later phases, like for example, during the semantic analysis phase. But ideally speaking, we should not have these kinds of situations in our programming language. They indicate some kind of language design problem. Okay, you need to have a compelling reason for these kinds of ambiguities to arise in your programming language. If there are no compelling reasons, then you have to fix your language. You have to solve this problem at the language design phase itself. Okay. So finally, a couple of things that I would like to highlight is like, for example, in your programming language, in C, before you use a variable, you have to declare the variable. Okay. So can you enforce that constraint using context-free grammar? Is it possible for you to enforce the constraint that a variable has to be declared before it is used? Is it possible to enforce this constraint using the context-free grammar? Okay. And so other interesting thing is, like if you make a function call, the number and the type of parameters in the function call may not match with the function definition. Okay, is it possible for you to enforce this constraint that the method, when you make a method call, the number of parameters and the type of parameters match the signature of the function or the prototype of the function? Is it possible to do it using context-free grammar? So I want you to think about these two questions. And so if it is not possible to handle these using context-free grammars, then how can we, where and how we can handle these two questions or two problems, address these two problems. With this, I conclude today's lecture. Sorry, I went 5 minutes overboard, but I thought this logically brings us to the discussion on this topic so that we can start the next topic in the next